OK, so thank you very much, everyone. As Deborah said, my name is Hal Finkel. I work here in the science group at ALCF, at Argonne's computing facility. And I'm going to talk to you about using LLVM and Clang on the KNL. I'm going to give you an overview of where we are, what LLVM and Clang are first, I suppose, and then how this relates to the KNL, and what features are there and what features aren't there, and where we're going to be going in the future. So this way. All right. So just to provide some very basic background, so LLVM is a compiler infrastructure project. It is a project which is designed to make it easy to create compilers, to create programming languages, to create just-in-time compilation systems, or debuggers, or linkers, or any number of other things. It's most well known at this point as a companion, as the building block for Clang, which is the C and C++ compiler that is shipped as part of Xcode on everyone's Macs. And Clang is, of course, now available on many platforms, from Windows, Mac, Linux, all these kinds of things. And it goes along with a whole bunch of other sort of companion projects, C++ standard libraries and such, to provide an environment in which you can use modern C++ programming techniques, or C, or whatever you'd like. We don't quite have Fortran yet, but we're working on that. And so this compiler has been increasing in popularity, but it isn't really well known yet as an HPC compiler. However, a number of companies and other organizations have been investing a lot of money in LLVM and Clang and related things in order to bring it up to speed in this regard. And so, in some sense, this is something of a status report. We've been using Clang and LLVM here at the ALCF on our Blue Gene supercomputers for some years now. And we're obviously still interested in having it on our KNL systems as well, and later on our KNH systems, et cetera. Oh. Oh, buttons. I'll do this. OK. So briefly, so what is LLVM? So for those of you who, just as an aside, LLVM has been around for nearly a decade at this point. It doesn't really stand for low-level virtual machine, although perhaps it did at one point. It never made a very good virtual machine, but it made a pretty decent compiler. So, and the way that it works is internally it's divided up into different phases. And one of the really unique things about LLVM is that it has this well-defined intermediate representation, which is targeted by various front ends, like Clang for C and C++, but also by a number of other front ends for other kinds of languages, and in fact can also be used as a just-in-time compiler. And interestingly, although I'm not going to talk about this right now, we do work with at least a few science applications that are using this directly in order to do things like JIT kernels at runtime. It's an interesting topic, which I won't get into. OK. But the most well-known front end for LLVM is Clang. Clang provides a front end supporting C and C++. It supports all the latest C++ standards. It is primarily developed by Google at this point, with contributors from Apple and lots of other places. And interestingly, it supports. So I mean, obviously, it's a compiler, and so it can do code generation to produce programs you can run. It also has a really neat static analysis system built in, which can generate nice sort of HTML formatted reports of your source code that point out things you might want to fix. And there's an interesting project that's been integrated now from the University of Hamburg, which does MPI-specific analysis in the static analyzer. So this is something that's worth looking at. Oh, right. This button doesn't work. OK. but okay, so here we're going to talk about Knight's Landing. So just briefly, there are a few components in the LLVM infrastructure which are perhaps most relevant for running on Intel Knight's Landing. I'll point out that you can use LLVM and Clang to compile code for the Knight's Corner architecture, but LLVM doesn't support the vector instruction set on that machine, so it's less useful in that regard. But for Knight's Landing, we have AVX512 support. Intel has invested a significant amount of effort in making sure that LLVM supports AVX512. It's probably the largest single addition to LLVM's x86 backend ever. I don't know. I don't know how many people realize this, but AVX512, the instruction set, is huge, and supports many things. Okay, so that's there. And Clang also correspondingly supports all of the same AVX512 intrinsics, or almost all of them, and we're aiming towards all of them, that are supported by the Intel compiler and GCC, et cetera. Actually, maybe no et cetera there, but nevertheless. And I'll also point out that OpenMP4 is supported in Clang. That was another thing in which Intel invested quite a bit of effort. And so OpenMP4 has these sort of two somewhat orthogonal components that are relevant for us. One is the actual parallels and pieces, and the other is the SIMD directives. So both the SIMD directives are supported along with the thread level parallels and stuff that you would expect from OpenMP, and so all of this is there and useful. Moreover, LLVM's OpenMP runtime library is essentially Intel's OpenMP runtime library. Intel contributed the source code for their OpenMP runtime library to the LLVM project a couple of years ago at this point, and the Intel OpenMP runtime team has been actively maintaining this part of the code base. So this is so one of the nice things about this is that it means that the OpenMP code that is produced by Clang is ABI compatible with Intel's OpenMP runtime. So you can have OpenMP code that you compile with Intel's compiler. You can have OpenMP code that you compile with Clang, and you can link them all together, and that actually makes sense as far as the OpenMP threading goes. The OpenMP runtime library also has a libgomp compatibility layer, so stuff that you compile with GCC also can kind of fit together with this, which is nice. So LLVM has these runtime components. There's a particular note are the sanitizers, address sanitizer, et cetera. These are nice instrumentation-based debugging tools, which should be quite nice to have on the KNL and work there. And finally, I just want to point out that Intel's vector math function library, Intel has actually already contributed pieces of this to GCC and glibc, and is in the process of doing the same thing for LLVM. So, but the code that targets this, at least in a basic sense, is already in Clang, and I'll say something about this later. Okay. So just quickly, so this is a graphic from Avinash, who is the Intel KNL architect or what have you, and just to show you, so LLVM obviously already has support for all of these things, and at this point has support for these things as well, although some of them only in intrinsics. So these things down here are mostly only supported in using intrinsics, but we do have auto-vectorization support for the AVX512 instruction set, and most of the features that AVX512 supports are already supported by LLVM and its auto-vectorization transformations. And that includes, obviously, the additional vector registers and all these kinds of things, and the embedded broadcasts, and scatter-gathers, and masking, and all that stuff. All right. So one thing I'll point out that LLVM does not do yet is this. So AVX512 has these nice conflict detection instructions. We have intrinsics for them, I believe. But the auto vectorization support does not yet do it does not yet use the automatic conflict detection instructions to assist with auto vectorization. That is something that the Intel compiler does currently. And we're currently in the LLVM project working out how to add support for this, but it's not there yet. It is. I will point out, however, that there is some trickiness here in doing this correctly or optimally, I should say, because if you have loops in which you have a lot of conflicts, statistically speaking, it might still be better to use some other technique than these instructions, and so we're working out how to work through all those details. Okay. Smart masking. I'm just going to kind of skip past this for the time being, and say that a lot of the sort of basic things that AVX512 supports, like embedded broadcast, et cetera, these are all already supported by LLVM. Okay. And as far as this goes, I want to just sort of provide a simple example here and talk about why this masking sort of matters so much and where we stand as far as this goes. So so here's a kind of prototypical loop that I work with a lot in science applications. Particle-based science applications, and it's a prototypical loop for something that we were not able to auto-vectorize previously, but with the addition of masking and other things, we now can auto-vectorize these kinds of loops. The issue here is that in this loop you have this array out, which is only conditionally I should say you have this function here, some access to this array here, which is only executed conditionally, right? So it only is executed if this condition is true. And previously we weren't able to auto-vectorize accesses like this because in order to auto-vectorize it, you would essentially have to always access these elements and then evaluate the condition later on a whole vector of them. And now we don't need to do that anymore because even if this array isn't actually the same length as the others, which was the underlying issue, why we couldn't auto-vectorize it before. Now, even if it's not the same length, even if some of these accesses would be illegal when this condition is false, we can auto-vectorize it anyway because we can mask off the accesses that correspond to elements for which the condition is false. And this kind of prototypical situation is really fairly common and is a really nice addition of AVX512 and is a really nice enhancement to our ability to auto-vectorize things. Okay. All right. So this is my sort of reality check. So the reality check is the following. So I took part of the TSVC auto-vectorization benchmark. This is an auto-vectorization benchmark that has some 100 number of tests, and they wouldn't all fit on a slide, obviously. So I have just this one particular part of it. This auto-vectorization benchmark is something that was created some number of years ago as a collaboration between some academic groups and the IBM compiler team in Toronto. And so here I've run the benchmark on the Intel developer access box that sits in my office, compiled with some various compilers. These were all of this was done at -03 with strict IEEE floating point turned off and targeting the KNL using appropriate compiler flags. And using relatively recent versions of the relevant compilers. So I do want to say that while LLVM has support for AVX512, we don't have any work upstream for LLVM yet that specifically tunes for the KNL. So this is something that is going to have to be ongoing work at this point. And so even though we don't actually have any specific KNL tuning, this is all just sort of generic AVX512 code generation. I actually find it interesting that the numbers aren't crazy. So here, so the yellow bars, I don't know if you can read this from the back. The yellow bars are some relatively recent Intel compiler. The red here is GCC 6.1, and the blue bars are some trunk version of LLVM from just a day or so ago, and here the vertical axis here is the running time of each of these tests in seconds. So smaller is better, and so my takeaway from this actually is that the numbers aren't crazy, which is nice, and the compilers actually are all fairly similar-ish, but there's a fair amount of scatter. I mean, my prediction is that as the compiler technology for AVX512 matures and as the relevant architecture tunings improves for these various compilers, then this scatter will reduce somewhat. Yep. Over here? OK, well, I will qualify. So what I mean is that in each of these, for each of these tests, I shouldn't say that exactly. For most of the tests, the time that for the benchmark time for the LLVM build is similar to either the GCC number or the Intel number. That was what I meant by not crazy. So I mean, the thing is that obviously, for different tests, different compilers are going to make different code generation assumptions, and some of these things are things that will just be fixed. Like I imagine this is probably something that will go away. This last one, but yes, that's what I mean. Fair enough. OK. So so let me following. OK. So a couple of other thoughts. So one is that in general, I have found the OpenMP for SIMD directives to be useful. I obviously find them useful on other systems as well, but they are definitively still useful on the KNL. As is putting restrict where appropriate on function arguments. That helps with LLVM. And using fast math when you don't need strict IEEE conformance. This is especially important if your code has to do anything like square roots or reciprocal calculations, because AVX512, like most other modern vector instruction sets, have estimates for reciprocal square roots and reciprocals that you can use, but not if you need actual strict IEEE conformance for your calculations. They are much faster than the full the full computation of the square root or what have you, and so that's quite important as far as that goes. The other thing I have here is this is the flag that you would need in order to make LLVM generate SVML calls from the auto-vectorizer. So that means specifically if you have a function, if you have a loop or what have you that has calls to something like cosine in it, or sine or tangent or whatever, and you would like the auto-vectorizer to vectorize it, then it needs to have some vector version of that function to call. And so if you have SVML, or you have a very recent version of glibc, or whatever it is that also has these functions in it, then you can pass this flag and then make sure you link to the right library, and you'll get your loops to vectorize. This is obviously quite useful in many contexts as well. One other parting thought, which I'll mention, but only because threading is so important on the KNL, and I didn't put it on the slide. So LLVM has these sanitizer libraries, right? Address sanitizer and memory sanitizer, et cetera. Most of these things are very much like Valgrind, only much faster, because with the sanitizers, the checks that are done are actually compiled into the program and get optimized along with the rest of the program. So the sort of relative slowdown of your program in the mode where it's being checked for out-of-bounds array accesses and everything else, that slowdown is much smaller than with a program like Valgrind, which has to sort of do everything after the fact by interpreting things. One of the sanitizers that's provided with LLVM is called the thread sanitizer. And the thread sanitizer specifically checks for race conditions and other things. And in fact, there's some ongoing work, collaboration with folks from Lawrence Livermore National Laboratory to make sure that the thread sanitizer properly supports OpenMP. But nevertheless, it's useful even as is. So you can pass -f sanitize equals thread, and you can compile your code, and it will check for race conditions and other things which can be otherwise quite tricky to find. All right. So that having been said, obviously most of the work that's been done to make this possible has been done by Intel, and so they get the thanks of me and many others, and obviously ALCF has been quite supportive, so I appreciate that. So at this point, if there are any questions, happy to answer. Okay. I think for, oh yeah, sorry. He asked what version of Clang do you need to get support for AVX512? So there's some AVX512 support that exists in older versions. I think that for useful AVX512 support, you need at least version 3.9, which is the version that was just released a few weeks ago. I've tried the AVX512 in some of the older versions, like 3.8, but you end up running into a lot of internal compiler errors and things. It's not worth your time. Okay. So this is a good question, and I work on Hack, right? So as you probably know. So I don't know yet, except for the following two things. So one is I have compiled Hack with LLVM and Clang on the KNL. Hack obviously has forced kernels of various kinds. We have like a C version, and we have a version that uses AVX512 intrinsics, and we have an assembly version and other things. So I can use that as a basis of comparison. But regardless of anything else, I use the sanitizers of various kinds to run and check for errors and make sure that the code is clean. And that in and of itself is a benefit, regardless of what compiler we use for production runs.
Are we always going to be using writing our own intrinsics for things that we want to be really fast?
So I don't know yet. I would like to say the answer is yes. I think that I mean, with hack in particular, the AVX512 instruction set is really the first one that gives the vectorizer all of the tools necessary to auto-vectorize the relevant kernel. And so I would like to think that at some point the compiler will generate code that is as good or better than what we could write using intrinsics. You know, we'll see.
Thanks.
Sure. Yeah.
Heard that LLVM will have support for Fortran. So, what are the plans?
Good question. What are the plans? So there's an ongoing collaboration between several of the Department of Energy labs and PGI, which is now part of NVIDIA, to release as open source the PGI Fortran front end as a front end for LLVM. This is ongoing work, but we expect to have news pretty soon. I mean, I'm actively involved in this collaboration, so progress is definitely being made on that front, and I certainly expect within the next year that we will have a viable Fortran front end for LLVM as well. Now, one thing about that is also that once we have the Fortran front end, there's also this process of sort of teaching the optimizer about all of the additional things that you get in Fortran, say, that you don't get from C or C++. For instance, in Fortran, the compiler knows how to get the length of all the arrays, which is quite useful for doing vectorization and other things. Actually, it doesn't matter quite as much with AVX512 as it has in the past, but nevertheless is still useful. So once we have the Fortran front end, and there'll be some work to improve the optimizer to take advantage of some of the Fortran-specific things that you get from it, or things that you get from, I should say, at least things you get from Fortran that you don't get from C or C++ directly. But yeah, I mean, this is definitely ongoing work, and we should have some news on that soon. It should support OpenMP, yeah. Yeah.
I'm too late.
Yeah, no, that's okay. He asked if the Fortran front end will support OpenMP directives. The answer is yes. It should support OpenMP directives. I don't know. I mean, it should at least support OpenMP directives that we care about in the KNL context, which are the ones for the host side parallelism. I don't yet know what the plans are for offloading for accelerators and such, but it will target LLVM's OpenMP runtime library and should have all of that relevant support.
Well, with no more questions, let's thank Finkel again. Thank you.